thank you for that. Oops, careful. Thank you for that very kind introduction. Yeah, okay. Thank you for that very kind introduction. And I don't know if I will live up to all of this, but I am going to talk. My understanding is I talk for about half an hour, and I probably should put my clock out here because I can go on for forever if, yeah, but I'll try and keep it to that. So again, I want to thank you, and I'm going to talk a little bit. So the book, I'll mention the book a little more. The book describes a lot of many topics, including the subject of this little film, particle fever, which you mentioned. But I'm going to just focus a little bit on Einstein today, and sort of what Einstein did, what made him so great. So let's make sure I can use this. Yes. So you mentioned University of California at Santa Cruz, where I was for 30 years, and I'm not sure how many of you are familiar with it. But say one thing I left out a picture. It sits amidst towering redwoods looking over Monterey Bay. It's a very spectacular setting. And before retiring with Melanie, my wife, many of you know, Rabbi Melanie Aaron, to Washington in 2020, I had a wonderful career at the University of California at Santa Cruz. And my understanding is that Clark Kerr, a name you may know as a leading figure in American higher education, had a vision for the UC Santa Cruz campus as a center for humanities and social sciences. And it has been that, but for serendipitous reasons, it has been a scientific powerhouse. And I really had a very wonderful career there. So it was established in 1965, and it excelled in a number of areas. Ocean sciences, well, it was right by the ocean, sort of obvious. Astronomy grew there in something called the Lick Observatory, which is the major astronomy center of the University of California system. Centered there mainly because there was sort of bad blood between people at Berkeley and some of the people who were going to head it up. So they wanted to be somewhere else. In physics, you mentioned the Stanford Linear Accelerator Center. That was also just newly established and was a big draw. And other fields thrived as well. Now, I came to California. I mean, you mentioned I was at City College in New York. It's a place that some of you are probably familiar with. And we needed to live near Melanie's synagogue. So my wife is a rabbi, as many of you know. And I had a long commute over the Santa Cruz Mountains. And from the start, I had a carpool. And the carpool itself was rather interesting and features a little bit in the book. It included two high-energy experimental physicists. One was a member of the local conservative congregation, and he'd been born in a DP camp in 1946. The other was the son of a German military officer who was executed for his role in the 1944 attempt to assassinate Hitler. And interestingly, these very different and strikingly different backgrounds, they were quite close friends. There were also two astronomers, one George Blumenthal, who eventually became the chancellor of UC Santa Cruz, and another was an expert on planets and especially played a role in the understanding of extrasolar planets. Okay, so I had a lively beginning and end to each day. Now, as far as this book, the book which This Way to the Universe, this is something I started to think about several years ago. I wanted to communicate the exquisite understanding we have developed of nature, both at extremely small scales, things smaller than atomic nuclei, and very large scales, things on the scale of the whole universe. And to convey the sense that we understand a great deal about our universe, but there also remain many big mysteries. So I talked to a friend of mine who introduced me to his agent, who dissed my proposal. So I got some advice then from a person named Rob Irian, who had then headed UC Santa Cruz's science writing program, a program which trains science journalists. And then by some good fortune, I met a man named Graham Farmiloe, who was the British author of a wonderful biography of a rather peculiar physicist known as Paul Dirac. Some of you may have heard of him. He provided some advice and criticism of my proposal, and then shared it with his agent, a man named Toby Mundy. There followed some development of the proposal, meeting with publishers, and then a great deal of work on the actual manuscript, all sort of during the COVID lockdown, guided by my editor at Penguin Random House, Stephen Morrow. So let's see if this works. Yeah. Okay, I hope I don't lose it here. So I just advertise the book if it comes up. There it is. Yeah. So this is the book, and I may need a hand getting back to the PowerPoint. Let's see. This one? Yeah. Sorry. Okay. That's great. Great, thank you. Thank you, sorry about that. Okay, so today I thought I'd talk a little bit about Einstein. Einstein, unlike anyone else in physics, looms in a particularly large way in almost any discussion of the subject. So here's a picture of him writing one of his famous equations of general relativity on a blackboard. And so let me just set the scene a little bit by describing a little bit what was physics like before Einstein. What did we understand about the laws of nature? So we had sort of Newton's laws of motion. So this describe how things like an object in motion stays in motion, and so on, things like that. And force is mass times acceleration, and gravitation. So Newton also proposed the law of gravitation. And someone was mentioning the apple falling on its head, and what Newton's great recognition there was not so much that things fall down. That didn't require a genius, but what he did recognize was that things fall in a universal way. So that an apple falls just like the moon falls towards the earth under the earth's gravity. That was his recognition there. So he had explained the motion of the planets with great precision, and he could understand things like motion of nearby stars, but the universe as a whole was a challenge. And Einstein emerged on the scene and reshaped our understanding of space and time. So Newton's laws, while very successful, describing many elements of nature, had certain peculiarities or flaws. So in Newton's laws, the motion of one star or planet instantaneously affects the motion of all the others. And this is called action at a distance. So if somehow you were to move the sun instantaneously, that would affect the motion of the earth. And that is, I say, it's called action of a distance, and it's almost ghostly. And this was a source of some skepticism from the very beginning. Newton appreciated the problem and was actually quite defensive about it. In fact, I remember in an essay, I don't even know why I remember this, but in my SAT in 1960, whatever, remember that this being discussed in some multiple choice question. Resolving this problem would require rethinking the very ideas of space and time, and this is where Einstein will enter. So Newton had this notion that time was absolute, and in fact he said so. So he says in the Principia, his great work, absolute, true, and mathematical time of itself and from its own nature flows equably without relation to anything external. Absolute space in its own nature without relation to anything stable remains also always similarly and immovable. So exactly what that means, I'm not sure. But then he says this other thing, absolute time is not an object of perception. The deity endures forever and is everywhere present, and by existing always and everywhere, he constitutes duration and space. Okay, so I think really what this is Newton kind of just, this is how it is, guys, folks. You know, it doesn't, these are questions which are just not to be really addressed. But Mach, who was a scientist and philosopher and one of Einstein's early heroes, wrote, absolute time is, quote, a useless metaphysical concept and cannot be produced in experience. Newton acted contrary to his expressed intention only to investigate actual facts. And Poincaré, a great French physicist, wrote, not only do we have no direct intuition of the equality of two times, we do not even have one of the simultaneity of two events occurring in different places. Now, Poincaré, this is actually close to what Einstein will say. And Poincaré had much of the mathematics of special relativity, as did another great Dutch physicist named Lorentz, but neither made the final leap that Einstein did. So they were still sort of wedded to this absolute space and time that Newton spoke of. So then along comes Einstein in 1905, and he developed something called special relativity. Okay, and so by that time, Maxwell's equations, the equations which describe the phenomena of electricity and magnetism, and in fact light, were well established. In studying these equations, Einstein realized that they do not admit an absolute time. There is also no action at a distance. Events at one time affect one another through the emission and absorption of light. And I'm using light, sort of generally, light might also mean radio waves or microwaves, X-rays, other sorts of waves, but some kind of radiation. And Einstein then developed his theory of special relativity. And with that theory, absolute time, in fact, was lost. Different observers measure different times on their clocks. Events which are simultaneous for one observer are not simultaneous for an observer moving relative to that observer. Okay, so all these things are rather shocking and non-intuitive at first. And crucial to all this is that Maxwell's equations involve electric and magnetic fields. Okay, so it's something, again, you may have heard about a little bit. Okay, so there's sort of something at every point in space and time associated with these objects. Okay, and in this space and time, he now calls space-time. So in fact, Einstein was attributes a lot of his insight to Maxwell's theory. Okay, he says of Maxwell in this field concept, a new concept appeared in physics, the most important invention since Newton's time, the field. It needed great scientific imagination to realize that it is not charges nor the charges nor the particles, but the field in the space between the charges and the particles that is essential for the description of physical phenomena. The field proved successful when it led to the formulation of Maxwell's equations describing the structure of the electromagnetic field. So this is Einstein's first relativity. There are really two relativity theories associated with Einstein, one called the special theory and one called the general theory. Okay, so this is his special theory. So he developed this in 1905. Okay, again, as I say, time became a relative concept. Okay, so this is really sort of the origin of this word relativity. Okay, who's looking at it, who's measuring it, determines sort of what the time is. Okay. And there was none of this action at a distance that was so troubling in Newton's theory. Now, a question he might have asked right away, but didn't, is, well, what about Newton's theory of gravity itself? How does that work? Okay, so Newton's theory doesn't look like Maxwell's theory. Okay, this theory of electricity and magnetism. It looks like it's got action at a distance. But he didn't ask this question right away. Instead, in 1907, he was asked to write a review. And while writing that review, he thought about gravitation. And he asked how one might write a theory of gravitation consistent with the principles which underlie his special relativity. It was hardly pressing a question experimentally or observationally at that time. So he had some guideposts in this, how to think about this. So for things which are moving slowly, slowly means relative to the speed of light. So even planets, they move fast, move slow compared to the speed of light. So things may move at hundreds or thousands of kilometers a second, but that's not like the speed of light. Newton's law, so for slow motion, Newton's law should be valid. There should be no action at a distance. Okay, the interaction should propagate just like for electromagnetism, they should propagate at the speed of light. And really critical was Einstein's focus on something he called the equivalence principle. Okay, so I mentioned in Newton's laws, there's F equals ma. Okay, this is a famous expression. The force is mass times acceleration. And the mass is something, in that law, it's called the inertial mass. It has something to do with the inertia of a system, its resistance to moving. Okay, and then there's a mass which appears in the gravitational law. Okay, so the force of gravity is proportional between the Earth and the Sun, for example, is proportional to the mass of the Earth and times the mass of the Sun. Okay, and that's called the gravitational mass. And what he realizes that those two are the same. Okay, and he realized that's a big deal, that it sort of relates gravity to motion, to how things move, how things respond to forces. Okay, so, oops. So he's launched with this, with insight into a struggle to develop this theory. It takes him about 8 or 9 years. Okay, largely because he sort of knew what he was after, but he didn't have the mathematical tools really that he needed. They were just barely available at that time to mathematicians, much less to sort of other people in other fields in science. Okay, so I say, after a long struggle, he realized that the equivalence principle, this equivalence of mass, of these two kinds of mass, required a reformulation of gravitation in terms of the geometry of space-time. The mathematics of the theory that he developed was challenging, and this was a big, as I say, a big part of his struggle. The mathematics remains a challenge even for a contemporary graduate student, but the underlying concepts are not so hard and are explained, at least I hope, reasonably clearly in my book. Okay. Now, critical to Einstein's picture is that the geometry of space-time is not fixed, but is determined by dynamics. In the presence of energy and momentum, stars, planets, gravitation itself, space-time, sort of in some kind of generalized sense, curves. Okay, so we can sort of think rather easily about how space being curved. Yeah, yeah. Sorry. It's being on the surface of moving on the surface of the Earth, which is a curved surface. We understand that, and sort of there's a kind of generalization of that which Einstein understood for space-time. And in fact, in some suitable sense, particles follow the shortest path between two space-time points. Okay, so he announces this theory in 1916. Okay, and he proposed some ways to test it. So predictions of Einstein's theory in most situations are almost the same as Newton's. And for most of the 20th century, there were really only 3 tests of Einstein's theory. One was associated with the motion of the planet Mercury, a slight anomaly in the motion of this motion, not accounted for by Newton's laws. Okay, and this was something he realized early on he could explain. Something called a gravitational redshift, a shift in the wavelength of light as it passes through a gravitational field. And a third was the bending of light by the sun. Okay, so because gravity acts on other things, gravity in particular pulls on light, okay, and alters the trajectory of light. And this third prediction was something that was subject rather quickly to an experimental or an observational test. So the British astronomer Arthur Eddington led an expedition to observe a solar eclipse. Okay, and in fact, there were 2 expeditions. The first one was blocked by clouds, and actually at that point, one of the ironies is at that point Einstein actually didn't have the prediction of his theory quite right, and he sort of lucked out. So the observations failed, and he'd corrected his prediction by the time of the actual observation of Eddington a little later. And when Eddington confirmed Einstein's theory, and it's that point actually that Einstein becomes very famous. Okay, so it's this observation of Eddington that he becomes a sort of superstar of science. Okay, but as I say, when I was a graduate student, there were really only these 3 tests still, and it was kind of, it wasn't something a respectable person spent a lot of their time on. There were other phenomena known to be possible. Okay, and an example is black holes, which many of you probably heard of. The collapsing stars might yield objects so dense that the force of gravity on light would keep the light in. Okay, the light couldn't escape. Okay, And for those of you who've seen the movie Oppenheimer, this realization was perhaps Oppenheimer's greatest contribution to pure science. So this is something actually Oppenheimer did as a young man. And ironically, he never followed up on it. It was, they say, one of his great pieces of work. Einstein also realized that one could think about the universe as a whole. Okay, and at some point in its history, the universe was extremely dense, space-time was highly curved, and there was, if you like, what we refer to as a Big Bang. Now, actually, this term Big Bang originates with the astronomer Fred Hoyle, who said this to make fun of the theory. He thought it was absurd. He was an advocate of something called a steady state model, but the name caught on. And in fact, some of you may remember a number of years ago, the magazine Science sponsored a little contest to rename the Big Bang. And no, Big Bang won. Okay. Another prediction of this theory is gravitational waves. These are, so you mentioned waves before. So there are waves of light, okay? And just as there are waves of light, in Einstein's theory, there are waves of gravity. So there are little ripples in space-time which move objects. So they provide a force on objects. Okay. Okay. So in the late 20th century and the early 21st century, though, all this changed. The sort of picture I had of as a young graduate student changed. Black holes have been observed and studied. Cosmology has advanced to great extent. So in the late 20th century, the cosmic microwave background was discovered. It was discovered by sort of accidentally by two physicists, Penzias and Wilson. I mentioned them because Penzias's daughter actually is a rabbi in Santa Cruz. But this radiation was discovered as pretty much by accident. They pointed an antenna they were working on. They were at Bell Labs in Holmdel, and they were pointing their antenna at a part of the sky where they expected to see nothing, and they saw this noise. And they tried to figure out what it was. They thought maybe they had all kinds of theories, including it was pigeon dung in their device. But eventually, it was realized that they were seeing radiation from the Big Bang, from about 100,000 years. The universe, remember, is about 14 billion years old. So 13, 14 billion years since the Big Bang. This was about 100,000 years after the Big Bang. Okay, and now it's understood and studied in great detail. Okay, another phenomenon, just sort of it's in our back pockets, is GPS, which all of us sort of live with in various ways in day to day. And GR is actually, general relativity actually is important in achieving the necessary accuracy of GPS systems. General relativity, I'm sorry. And gravitational waves were first inferred from pulsar timing, but they were actually detected in 2017, and they won the Nobel Prize. They were awarded the Nobel Prize in 2017 for the discovery. And in particular, what one saw was waves arising from colliding neutron stars and black holes. So extremely energetic events. So neutron stars are the end product of the collapse of certain stars. Okay, they're very dense objects. They sort of have the density of atomic nuclei. So they're as heavy as the sun, but have a size sort of smaller that would fit in between here and my house near DuPont Circle. Okay. All right. So this is just a picture of one of these gravitational wave detectors. This is the one in Louisiana. Okay, the discoveries were made by detectors in Washington State, Louisiana, and in Italy. Okay, we know people thought for a long time, and we now know that there's a black hole at the center of the Milky Way. Okay, in fact, there's this black hole at the center of most galaxies. Okay, large black hole, large measured in its mass, many times the mass of the sun. Okay, and this was suspected for a long time. And in fact, in 2000, I spoke at a conference right after a NASA administrator talked about a huge NASA project to image this black hole. And I remember this talk, it was a very slick talk. He had beautiful slides, and I was really embarrassed. I got up after him and I talked the slides with, with marker on a transparent pen on a marker. But in fact, shortly afterwards, okay, this black hole was seen through a beautiful small-scale project. Okay, and in fact, the leader of this effort was a physicist at UCLA named Andrea Ghez, and she produced an image of this black hole at the center of the universe, the center of the galaxy. And for this, she shared the Nobel Prize in 2020. So let's see, unfortunately okay, so I'll just talk another minute or two and then I'll open for questions. Okay, so one of the things that but you ask about the universe as a whole and things like the collapse, and so what Einstein's equations also opened up, and he recognized this as did others quite quickly, they open up cosmology. So we can contemplate with Einstein's equations the universe as a whole. Okay, and we need to do this though, the equations themselves are kind of complicated, and the universe is complicated, it's full of stuff. Okay. And so he needed some starting assumption, and he did something that to me, when I first heard this as a student, looked crazy. It's done something called the cosmological principle, which is that on large scales, okay, where large now, we have to decide what large means, but large will mean on the scale of many galaxies. Okay, the universe looks the same wherever you are. Okay, so wherever you are, the universe looks the same. This is called homogeneity. It's certainly not like what most of us sort of intuit the universe to look like, okay? And it looks the same in whatever direction you look, okay? And this is called isotropy, okay? It seems a bit crazy, but it's the simplest assumption one can make, and it turns out to be remarkably accurate, okay? So just to mention, prior to Einstein's general relativity and the observations of Hubble and others, there was no real idea of what the universe looked like on very large scales. So the existence of galaxies was just barely appreciated at that time. But Einstein's equations allowed scientists to ask sensible questions about the universe as a whole. Okay, and with assumptions about what the universe is made of at various epochs, we can write a history of the universe starting with a Big Bang and evolving to the present time and into the future. Okay. So Einstein was startled to discover that his equations implied a very dense, essentially infinitely dense starting point, followed by a steady expansion. He tried to modify his equations because at the time, nobody knew the universe was expanding. There was no evidence for that. But about the same time he did this, Hubble made his discovery that the universe is expanding. And the history of that discovery itself and how that evolved and what one was or wasn't known is really quite interesting. But shortly afterwards, this suggested that this picture of the expanding universe was correct. Okay, and so in fact, there are sort of few critical epochs in cosmic history. So at times less than 3 minutes, the light elements form. This is something we know a lot about, we understand a lot about. At times less than 100,000 years, matter was tightly packed together and the universe was very hot, and atoms and molecules were broken into their constituents. And it's that time when things actually come together, that this cosmic microwave radiation background comes from. And about 1 billion years after the Big Bang, stars form and begin to burn. And some of you may have seen, there's a headline recently from the James Webb Telescope of the observation of very early galaxies, okay, at this time of about 1 billion years after the Big Bang. Okay, so I'm just going to, this is a little history of the universe, but we don't have time for it. I mentioned some of the evidence, and in particular this cosmic microwave radiation background. This is Schiffer Penzias, the rabbi I mentioned. I think, oops. And I think I'm gonna, well, I should say we know a lot about what the universe is made of. Okay, the universe is made about about 5% of what we is stuff like us, is things like protons and neutrons and things made up in that sort. About 30% is something called dark matter, and the rest is something called dark energy. And this is, again, something that has become clear over the last 2 decades or so. Okay, and a lot of effort is going into studying these phenomena. Okay, so I think I'm going to stop there. Whoops, and open it to questions and discussion.
Thank you. Thank you very much.